Hello students, welcome back. The final topic of chapter 2 of our textbook is linear Diophantine equations. This is a branch of mathematics developed by ancient Greek mathematician Diophantus. I hope I pronounced correctly. And basically we are looking for integer solutions of an equation or systems of equations. Sometimes rational solutions, but that's really rare because, whenever we have finitely many rational numbers, we can always take the common denominator and look at only the numerator, which are integers. So, except for some very special case, possibly, or maybe not even that, we can reduce everything into integer solution problems. At least all the problems I know of are all about integer solutions. Here's some examples I took from the textbook, or our old textbook to tell the truth. Here's an example. 20x plus 50y is 510, where x and y are whole numbers. And as a matter of fact, precise language our textbook uses is like this. Stop the playback and read through the problem. So some traveler's check problem with some dollars and cents. No cents, just dollars. In any case, it can be simplified into this, or you can simplify this thing even further. Divide each by 10, and you're going to get that, and that's this equation. That's a algebraic equation that you have to solve within W. So this is an example of a Diophantine equation. Here's another problem here. This time you cannot simplify, and this problem is associated to this. Again, I took it from our textbook, old textbook to be precise. Stop the playback and read through. Okay, this time cents, no dollars, cents. And then here, this one is just a problem I made up. And these two are linear equations, so I wanted a nonlinear example, so I put it over here. Those are examples of Diophantine equations. Now, how about the solutions? Well, within W, there are not that many, so we can actually try manually. You see, if you have negative integers as well, then there may be infinite many solutions. But within W, if we simply check all the x values from 0 to what is half of 50, so 25, and then y value from 0 to 10, that's gonna cover everything. So we can just use brute force method to check those out. And like this, let's see, 2x plus 5y equals 51, or previously 20x plus 50y equals to 510 defines a line in the real space. So there you go, blue line, and it runs through some lattice points where x is between 0 and 25 and y is between 0 and 10, so that the lattice points are all in the first quadrant, and we have 5 solutions like those. And, this is something you can do by manual checking. 25 times 10, so 250 computations to do. For computers, that's a piece of cake. Here's an example that has no solution. 6x plus 15y equals 83 is this blue line, and in the first quadrant, there's no solution. Actually, you can prove that there's no solution at all in entire Z, but at least in W, you can check manually. So x value is the greatest integer, not exceeding 83 over 6, so that goes up to 14, and then y value goes up to 5. So there are not that many values to check. For computers, it's a piece of cake. How about the next example here? This is nonlinear, but we can bring it down to linear equations. We can factor x squared minus y squared can be factored into x plus y times x minus y. So x plus y must divide 171, and x minus y also is a factor. So we have two linear equations basically. X plus y divides 171, x minus y divides 171. Let's see, 171 can be factored further like this. 1 plus 7 plus 1 is 9, so it's divisible by 9. So divide by 9, what's left is, yeah, something like that. And then 19 is a prime number. So the structure is 3 squared times 19. And within W, clearly x plus y is bigger than x minus y. So x plus y must be the bigger factor, and x minus y must be the smaller factor. And they multiply into 171. So we can see 19 times 9. And then, let's see, 19 times 3, which is, what is 9 times 3? Okay, 57 times 3. Only those solutions. So bigger factor is x plus y. Smaller factor is x minus y. So 19 times 9, or 57 times 3. So what do we have? We have basically two systems of linear Diophantine equations. Graphically, here's a solution, by the way. So solving that, x is 14, y is 5, that's one solution. X is 30, y is 27, that's another solution. And here's a visualization. X squared minus y squared is 171. It's a hyperbola. And then we have all these solutions in positive, negative integers. But within W, we have only these two. This one here and that one over there. In first quadrant, we have only these two. And then the others are all coming from second, third, and fourth quadrant. And we don't have to go to infinity because the multiplication must end at 171. So we have finite bound. It doesn't go forever. Well, at least in these kind of problems, you could have checked manually at the very least. That's because we're bound in W. And then from there, maybe using symmetry or something, maybe we can extend further, think about those kind of methods. But of course, we are learning number theory, so we want a little bit more clever method. Here is a beautiful solution by Brahmagupta in 6th century, I think, 6th century or 7th century, I'm not so sure. Brahmagupta is Indian mathematician. Let D be the GCD of A and B, and consider the Diophantine equation, ax plus by equal to c. Then this equation has no integer solution if D does not divide c, and it has infinitely many solutions when D divides c. Let's go back here. Let's see, what is the least common divisor of 6 and 15? It's 3, right? 3 does not divide 83. So no solution. How about this one here? What is the greatest common divisor of 2 and 5? They're relatively prime, so it's 1. And 1 divides everything, so there's no consideration to be done. So it has infinitely many solutions. And of course, if we restrict only to W, then we have only finitely many solutions. So we can easily check those. And as a matter of fact, that's this example. I just mentioned those, but and do those on your own and then write those down. Not only that, we can go one step further as a matter of fact. If we have GCD1, or even if you start from here, ax plus by equals to c. Even if we start from here, if we divide everything by d, this can be a over d, which is an integer, and then b over d, that too is an integer, and then that's c over d. What do you have? We have another linear Diophantine equation, but this time the coefficients are relatively prime. I used up a, b, and c, so alpha x plus beta y equals to gamma, where GCD of alpha and beta is 1. So you see, the arbitrary case where we have D as a GCD can be reduced to the standard case by simply dividing everything by the GCD. So if you know how to handle the standard case when we have those coefficients relatively prime, then we have everything, you see. For example, if you have, oh, wait a minute, there was a good problem to begin with, as a matter of fact. Previously, we had this. And then what did it do? We reduced this equation by dividing by the GCD. That's precisely what we did here, dividing by the GCD and getting down to this. So if we begin from simplification, we can assume any well-posed Diophantine equation, any well-posed linear Diophantine equation can be reduced to the standard case where the coefficients are relatively prime to each other. All right? Of course, if D does not divide C, then such a simplification is impossible. In that case, no solution, which we can prove. But if possible, if there is solution, then those can be brought down to the standard case. And then we have infinite many solutions. Not only that, the solution is this form. X is some cx0 plus bt, and b is same b right here, and y is cy0 minus at, where a is the same a as this, when a and b are relatively prime. And then what are x0 and y0? The linear combination expression on Bézout's theorem. So GCD is 1, so we end up with x0, y0 like this. And how do you find out x0, y0? To remember Euclidean algorithm, you should be able to find it like that. And then one more. So what do we have? We have a complete solution. We have complete algorithmic solution. You can find x0, y0 like this through Euclidean algorithm. Remember that? We went through, oh no, not these. Sorry about that. We went through those kind of problems here, expressing those as linear combination. We went through those kind of problems. That's how you can find x0 and y0. And then one more step, cx0 plus bt, cy0 minus at, and we're going to get full solution. So we have complete formula. And that's for the standard case. And the general case is, dt does not divide c, then there's no solution. And then in this case, we have this kind of solution coming from the previous case, actually. Now, how to prove those? We're going to do that in the next video.